All right. All right, so what we looked at yesterday was extending the idea of double integrals to triple integrals. Now, with double integrals, being able to set up a double integral two different ways and being able to do them two different ways and having to reverse the order sometimes is something I expect you to be able to do. Triple integrals, on the other hand, I am going to be rather lenient with things. So for a triple integral one, I won't give you one where you have to choose a specific order, because it's a skill that comes with a lot of practice. Because figuring out the bounds is the hardest thing. So you remember with double integrals, we looked at ones where we might have had a function that we couldn't integrate first with respect to x, say, but once we did the inner iterate, it would magically become something we could integrate with respect to y. That's not magic, that's design, because I'm giving you ones that you can do. So triple integrals, that's actually much harder to do. It's harder to see if you will be able to do it or not, depending on the limits. Figuring out the limits, as I said, is the hardest thing to do. This example that was in the lecture notes, this one, is an example of about as hard as it would get, right? This is a hard one, right? And setting this up all 6 different ways is a lot of work. A couple of the ways require 2 integrals. The type of questions I'll give you with triple integrals either will be one of 3 different types. I will never give you one where you'll be forced to change the order, right? To handle the function you're integrating. I won't give you ones like those, like with double integrals where we've got to reverse the order. But there'll be 3 types. Either it'll be one like this, right, and you just do it, right? You don't have to draw, don't have to change the order, you just do it in the order I've given you, right? Or there'll be one like this where I will provide the picture, right? So because this one's a bit hard to visualise. Or if it's one I would not provide the picture, it would be one like this, a simple one, right? So what I want to do this one is I'm going to do this one a different way to the way I've done it in the lecture notes. So just to rehash what we were doing. So this is a relatively simple one. I've got to evaluate a triple integral. Here I'm integrating a function, so I'm not asking for the volume of this. It's basically like a pyramid on its side. Right? I'm not asking, if I was asking the volume of it, I'd be integrating 1. What this is this is a function of 3 variables, although there's only z there. It is a function of 3 variables, so it sits in 4-dimensional space. You're looking for the 4D volume bound by that surface that you can't visualise, that sits above that region in the 4th dimension. You have no frickin' idea what you're doing, right? No one does, right? You can't visualise it, but we can go through the mechanics of it nonetheless, right? So here we've got a triple integral. I've got to evaluate this over a solid bound by the planes x equals 0, y equals 0, z equals 0. So that's basically just the 3 coordinate planes. And this plane x plus y plus z equals 1. And even I can handle drawing that, right? So this is basically the region here. Now you've got to decide what's the best way to go, right? So here, for example, I've picked a way immediately, but I want to redo this one by thinking, imagine you're sitting inside, how would you set it up? Because here I haven't told you which order to do it, the order is your choice, right? Right, let's actually do this one. Right, so what have we got? We've got to do, got a triple integral over some z, right, and basically, right, so I'm drawing it so x is coming out of the page. Right, and this is the plane. Right, and the back ends are the coordinate planes, the x equals 0, y. So the x equals 0 is the page, y is 0 is that plane, and z is 0 is that plane. So it's like a pyramid on its side. Right? Easiest way to do these, even if it's a simple one like this, imagine however you've drawn it. So I've drawn it so x is coming out of the page. Right? Imagine you're a little bug sitting inside somewhere. Right, and I give these names. So, as simple names as I can think of. I mean, there are other ways to do it. I find this the easiest. Right? So imagine you're sitting inside in the way I've orientated it, right? So imagine this board is the piece of paper, right, and I'm looking out the piece of paper. So that's, hang on, how have I done it? X front, X back, Y from your perspective, Y left, Y right, Z up, Z. So if I'm sitting inside and I go, all right, I look up, what do I see? I see the plane, don't I? Yeah? So Z top is just this solved for Z. Yeah? I look down, what do I see? I see the plane Z equals 0. Right? I look back, what do I see? I see the plane X equals 0. Right? I look front, remember I'm sitting inside this thing, I see the plane, don't I? Right? So this solves for X. Yeah? I look right, the way I've drawn it, I see this part of the plane. Right, and I look left, I see the plane Y equals 0. Right? So once I've figured all that out, then I can choose how to do it. Right? Now in the one in here, I've decided to integrate with respect to Z first. This one's pretty straightforward. Excuse me, so it doesn't actually matter how you do it. Right? So I'm just going to do it a different way just to convince you get the same answer. Let's say, just for the hell of it, I'm going to integrate, what am I integrating? Z. It doesn't really matter. Let's just do X first. Right? So if I decide I want to integrate with respect to x first, so I can see x goes from 0 right? So in other words, what I'm doing is my first iterate is going to be and once I've done the first iterate, I'm down to a double integral. Right? But now I've got to figure out what does this region R look like. So if I'm integrating with respect to x first, I want to squash this into the page. What does its projection look like in the YZ plane? Right? And hopefully you can see it's a triangle. Right? So if I squash this into the page, right, you get basically this triangle, this with x equals 0. Yeah? So once I do that projection, because I've decided to integrate with respect to x first, right, now I've got to do the double integral but over the YZ plane. Right, and it looks like this. So this will be now the line, right, which is basically the projection of this at x equals 0. Yeah? And of course this is 0, 1. Right, and then I could do this two ways. Then you've got the double integral, you could do two ways. You could do a small sweep in y, then a big sweep in z, or the other makes no difference, you see. Right, so I'm going to do it like this. Right, my first iterate, I've already decided. This one, small sweep in y, so y goes from 0 to 1 minus z, and then z goes from 0 to 1. Right? And what am I in? So I've chosen to do dx, dy. Right? And notice that this looks totally different so far. Right, here I decided to do z first. Now this is zyx. So all the limits will be different, but the final answer should be the same, provided you could do the integral. And with triple integrals, I'll make sure it can be done. So although there are 6 choices, right, none of the 6, unless you've got to split it up as 2 integrals or something like that, I'll make them so that one of them won't work. No, I won't make them so one of them won't work. Right? It won't matter. You see, it won't be like double integrals where I might trick you, where one way's doable, one way's not. With triples, I won't do that. All right, so now that we've got it set up, let's just do it. And hope, and fingers crossed, and check my algebra as I go, because if we don't get the same answer, have I stuffed up already? Yes. Oh yeah, I have stuffed up already. All right. All right, so let's do, so integrating z with respect to x. Right, that's like a constant times, a constant, which integrates a constant times x. And as I often do, I actually explicitly, so I don't mix them up, right, because I used to do that all the bloody time, right? So, just the fundamental theorem of calculus, you get, basically you just get z times right, so if I clean this up to make it easier to do the next iterate, that's basic, what is it, z minus z squared minus, right, or zy, it makes no freaking difference, of course. I usually, it's always that order x, y, z, so I do it without thinking. I just put x's first and what, of course it makes no difference. Right. Then the next one, now we've got to integrate this with respect to y. right? Right, so imagine it's a constant minus a constant minus a constant times y. Yeah? Do this. So what have we're replacing, so y not, see, the other problem is this gets tedious. Even this simple example starts to get tedious. All right? If you expand all this out, let's do it carefully. Right, so I've expanded the 1 minus z all squared times z in one hit, and hopefully I haven't stuffed it up. Now, what do we got here? So, one of those goes with one of those. Z minus a half z, that's a half z. That's that one and that one. What have I got, a z squared? I've just got a z squared on its own. Z cubed minus that, that's a half z. Right, then I integrate this. No need to put z equals now because I'm out of variables. You can though, of course. So essentially you get a quarter minus a third plus an eighth, which is, oh, I can't use 8. What do I need? 24, don't I, with the 3. So, so what's that? That's 1 on 24. Yeah? All right, and of course, here I've done it a completely different way. Right, so all the intermediate steps look different. All right, but all right. So these ones, as I say, either it's going to be 3 types. Either I just give you a problem to solve. I won't ask you to change the order or anything like that. So if I give you one like this, it's doable the way I've given it, unless I've stuffed up. Or without a diagram, they'll be very simple ones like this, right? Or they'll be complicated ones like in the lecture notes. As I said, the one in the lecture notes is probably as hard as it's going to get. That is a hard one, right? Because working out the bounding curves is difficult, right? Okay. Now, there's one application, and then I want to go through another example. There's a couple of, just as single variable integrals have uses, like, we use them to calculate areas, but we saw we could calculate lengths of curves and things like that. Double and triple integrals have lots of uses as well, and one in particular that's useful is something for centre of mass. So who's done any sort of mechanics or statics type stuff? Where you've got to, say they give you a shape, I don't know, like a pyramid or something, and you want the centre of mass, and there's usually a formula, isn't there? Some people know what I'm on about. You get this, a list of solid shapes, and here's the coordinates for the centre of mass. Yeah? Where do those formulas come from? Well, they come from integrals, actually. Right? And this allows you to work out the centre of mass of any shape, provided you can describe its bounding curves as functions. And it also will handle things that are not uniform density. Most things, we do are, the ones we do by hand, but it allows it to be not a uniform density. So we define something called a mass density function. This tells you how the mass varies through a solid body as you move through it. Now, of course, if the solid body is uniform, the density function is 1. or its actual density, whatever the hell it is, right? But if it varies, if it's made out of different materials, so imagine you've got something that's heavier in one end than the other. How would you calculate the centre of mass? Well, you need a function to describe how its density varies, then you do this, right? And you do a triple integral on it, right? And that'll give you the mass. And you can see how it works. So remember, dV is a volume element. It's basically like dx times dy times dz, or some different order, but it's length times length times length. Right? So that's like a length cubed times a density, which is mass over length cubed. Makes sense, doesn't it? Right? So given you can find the total mass of something by figuring out this triple integral, and then you can calculate its centre of mass by then calculating 3 more triple integrals. So you can imagine this is a lot of work, right, depending on the function. Right? But all the triple integrals will be the same. Once you set it up for one, you set it up for all of them. Right? You just got to do the algebra. Right? So you find these 3 things which we call the moments: x times the density function, y times the density function, z times the density function. Then you plug, this will give you the coordinates of the centre of mass. And so when you're doing these sort of problems in statics and you get all these formulas, this is where it comes from. Right? This is how we derive them from first principles. Now all of this is on the formula sheet. Right? You don't have to memorise any of these, you just got to do the triple if I ask you to do these. And quite frankly, I'm not going to be... This is 4 frickin' integrals. Right? I'm probably not going to ask you to do this very often, right? Because it's just tedious algebra. Right? You can also do it with things like thin plates as well, and they're double integrals, because you imagine that the third dimension is not really doing anything. Right? And very similar process. Now there's an example in here that does this. Right? But more so I want to go through how to set this up again. Right? Go through this one more time. This is an example. If this was one I'd give you the diagram. Right? Right, so we've got a solid body, it's basically got a constant density, right? So the density is 1. That means numerically its density and its volume are the same thing, right? Because density is mass over volume. So this thing occupies a region bounded by the parabolic cylinder x equals y squared and the plane z equals 0 and x plus z equals 1, right? And this is what it looks like, right? So I've got this parabolic cylinder, x equals y squared. The bottom bit is the plane z equals 0, and this plane that slices through it. So it's the enclosed solid body. It's what's sitting inside. Right? Basically, I'm asking to find its volume first. Right? Its mass and its volume are the same thing. Again, the hardest part here is setting up the limits. Right? So if I can't do both, can I? When you watch the recording, you see both these screens, don't you? Yeah? So if I do that, you'll see both of these, right? Sweet. Right. You just won't see me, but that's probably a good thing. Right. Let's work out the limits first. Right? So again, I've drawn it, so basically x is coming out of the... Imagine that I've orientated... x is coming out of the page, y's this way, z's this way, right? So if I do give you the diagram, take note of how it's orientated, right? I mean, z's always pretty much up and down. It's just some programs, you'll notice some of the pictures in the lecture notes are different to, say, these ones. This one I've taken from Maple, this program I've shown you a few times. They're orientated x and y differently. It depends on the program, basically. But almost always z's up and down. Right, so if x, again, what I do is I imagine, I do all of these the same way. Right, so I imagine I'm sitting inside. Now I've done it so x is basically coming out. Call them whatever you like. Right, I just keep it simple. Bottom, Z top. Right? And again, you have to figure these out no matter where you're sitting. You could be sitting anywhere inside this solid. So read right up the front or anything. That's what makes the one in the lecture notes so hard, because depending on where you're sitting and when you look up, you see two different things. Right? When that happens, that's a sure sign, do not frickin' integrate that way first. Right? That's a sure sign that, because you don't want to do this twice. Right? This one, however, you should be able to see from the picture, although the picture's not great because it's a scan, right? Obviously in a test it would be a much nicer picture than this one. Right? But you sort of imagine that no matter where you're sitting inside the solid, when you look up, down, front, back, left, right, you're hitting the same things, yeah? Right, so it doesn't matter where you're sitting. So imagine you're sitting in the middle. Right, if I'm sitting in the middle of this thing and I look, let's look up first. So I look in the positive Z direction, I hit the plane, don't I? Right? So the plane is x plus z equals 1, so this is 1 minus x. Right, just solving x plus z equals 1 for z. When I look down, I see the plane z equals 0, don't I? Right? Now, if I look forward, right, so looking out of the, I'm sitting inside looking out of the page, I hit the plane again. And I'm looking in the x direction, aren't I? Right? So this is, right, the plane x plus z equals 1 solved for x. I look back, what do I see? I see the back end of the parabolic cylinder, don't I? Right? So x back is y squared. Yeah? Now, if I look left and right, so I'm looking in the y directions, what do I see? I just see the walls of the cylinder, of this parabolic cylinder, don't I? Right? So y left, which is in the positive direction, that's right, we're solving this x equals y squared for y. Yeah? And of course one side's a positive square root, one side's a negative square root. Right? Then from here I have to decide what's the best way to go. Well, this one, you can probably see it doesn't really matter. Yes, there are square roots in there, but they're nice ones. Right? So they shouldn't cause a problem. Basically up to you. Right? Pardon? Y positive is to the right. Yes, it is. Thank you. Yes. Yes, it is. Idiot. Me, not you. Yes. Thank you. Right. So then you could set it up. All right, this is now, setting it up, that's only part of the thing. From this part, we see, well, it's probably not too bad how I do it, but now you've got to think about when you've decide your first iterate, then you have a double integral. Right? So not only do I need to take this into account, I need to take into account what does the region look like when I project it into each plane. So if I decide I want to integrate with respect to z first, I squash this way. What would it look like? Right? Well, it would just be a parabola and a line, wouldn't it? Right? Imagine you have a press that's pressing this thing down. Right? So it would basically, essentially you're laying down this parabola into the xy plane, and then this is the line x equals 1. Not too bad. What if you decided to integrate with respect to y first? So I squash it this way. Right? Hopefully you could figure out that that's going to become a triangle, isn't it? Right? So if I squashed it, it's basically this triangle bit. It's shadow. That's not too bad either. What if I decided to integrate with respect to x first? So I'm going to squash it into the page. Right? Then what you do, you'd be flattening that parabola down into the YZ plane. Right? So they all don't look too bad either, but probably ones with triangles are nicer than parabolas. Right? So why don't I decide, all right, I want to integrate, I'm decided then, I'm going to integrate with respect to y first. So from here, this tells me, right? And then in the xz plane, right? And this is just right. So that way is not too bad, right? Then you could do the next one though. Okay, then I first iterates with respect to y, and then I could, okay, and now I've got x going from, say, what, 0 to 1 minus z, and z going from 0 to 1, or I could have z going from 0 to 1 minus x, and x, you know, not too bad. But what if you wanted to do it another way? I want to do it, there's a certain way I want to do it, right? Hang on, where am I? Yep, that's... Let's say I instead, if I was going to do it... Right, let's say, just for the hell of it, I've decided I want to integrate with respect to x first. Right? Now, so I can see from this part that that means that x is going from... Right? And if I'm going to integrate, I'm squashing this into the page, right? So you should be able to see it's something like this, yeah? Right? Can everyone see that? What's the equation of that parabola? What would the equation of that parabola be? Right, now here you have to be careful. Right? Well, that parabola is basically the intersection of the parabolic cylinder x equals y squared and the x plus z equals 1. Right? Now, a lot of the time for projections, you think, well, if I'm integrating with respect to x first, it's basically a slice at x equals 0. That gives you y squared equals 0 and z equals 1. That's not right. Right? So here with this one, you have to be careful. The intersection of those two, x equals y squared, and x is essentially y squared plus z equals 1. Right? So this is actually... Right? That's how I'd figure out that bounding curve. However, you then go, well, why the frick would I worry about that? The previous way was easier. Right? Right, so sometimes you have to be careful to figure out the bounding curve. You can see from the diagram, you know it's a parabola of some description, right? And all this information is here. You just have to think about it carefully, depending on how you want to do it. Right? Right, but that's what this one looks like. Right? So you could set this one up. If I integrate with respect to, let's now go through it. If I integrate with respect to z first, z goes from 0 to 0 to 1 minus x. Then in the xy plane, this is just a parabola y squared and the line x equals 1. Right? And that's coming from, if I imagine this squashed down, you can see the line x, where the line x equals 1 comes from. That's where, because you've got that plane x plus z equals 1. When does that intersect the xy plane? When z equals 0, that's x equals 1. Right? And then the parabola you're squashing down, because that has no z dependence, that's where you get that from. Right? So you could then do this small sweep, big sweep either way. You could set it up as one of those. Right? If I decide I want to do x first, right, that's the one I've just done. Right? And that's what the projection looks like in the YZ plane. And then I could set that up two ways. Or if I integrate with respect to y first, that's my massive sweep in y, and that's what the projection looks like in the XZ plane. That one's probably the easiest because, you know, triangles, that's nice. Right? And all 6 are the same. Right? And I've cheated. Right? And just given you the answer. Right? So I don't, when I give you these questions, I don't expect you to do an integral 6 different ways, but I do expect you to be able to set them up all 6 different ways, right? So all 6 can be done this way, right? And I've got them all here. I've cheated and used a maple to do it for me, just to convince you that all 6 give exactly the same answer, right? But this one's not too bad, doesn't matter which way you do it. They're all pretty similar, okay? So this one is one where, as I said, if I gave you this sort of question, this is one where I'd give you the diagram. As I said, this is something that comes with practice. So before we move on to the next thing, which is change of coordinates, what I'd like you to do is, I asked you to go through this example. This example is actually very hard. This is as absolutely hard as it will get, right? What I'd like you to do instead is, this is one where I would not give you a diagram, right? So I've done this one way by hand and one way in here. Pick a third way, right? And do it. You do it all 6 if you're keen, right? You know what the answer's going to be. Right, and also work through this one, but as if I'd given you the diagram. Like if you didn't follow the one in the lecture notes, work through these 2, then have a go at the one in the lecture notes again. Right, the one in the lecture notes is a hard one. Okay, but this is a skill that comes with practice. All right, so I'll leave it there. Please do work through those. Right, and we'll do the last. We'll switch topics now and do change of variables in the 3rd lecture. All right, and I'll see everyone on Thursday.